Bismillahirrahmanirrahim. Welcome to MMH classes. Uh, Today we are going to begin with IGCSE GCE Computer Science series. We will be discussing paper 1. We're starting with paper 1, Theory of Computer Science. And the first topic is data representation. And the subtopic for today is binary systems, right? This is the syllabus for binary systems. These 4 points are to be studied. Recognize the use of binary numbers in computer systems. Second, convert positive denary integers into binary and positive binary integers into denary. A maximum of 16 bits will be used, from 8 to 16, right? The minimum can be 4 and the maximum will be 16. Show understanding of the concept of a byte and how the byte is used to measure memory size. Use binary in computer registers for a given application, such as in robotics, digital instruments, and counting systems. These 4 points we will study in binary systems right today. First of all, the code for IGCSE Computer Science is 0478 and the GCE code for Computer Science is 2210, right? So let's begin with binary systems. First of all, what is data representation? Data representation is basically the methods used within the computer systems to represent information to be stored. All types of information stored in a PC, personal computer, in this or computer in the sequence of zeros and ones. This is very important. The data is stored in zeros or ones. Now, what does 0 or 1 mean? A switch in the on position can be represented by 1. A switch in the off position can be represented by 0. On is 1 and off is 0, right? The microprocessor makes use of transistors that basically identify voltage levels rather than any affirmative value in decimal number system. Therefore, a voltage level high or on is identified as 1. A voltage level of low or off will be identified as 0, right? Some hardware may use different mode of identification for binary number levels, like in the case of a CD-ROM. Certain microscopic black spot will be considered as binary number 0, while a shiny spot reflecting light will be considered as on or 1. So basically what we get to know is 0 on is 1, off is 0, right? The next is a description about binary system. What is a binary system? The binary system is based on the number 2. This is very important, right? Thus, only the two values which we have studied already, 0 and 1, can be used in this system to represent each digit. Using the same method as denary, this gives the headings of 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. Why are we using 2? Because binary system is based on the number 2. Right. The typical headings for a binary number with the 8 digits would be this. First of all, we are studying 8 digits. This. 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 2 to the power 5 is 32, 2 to the power 6 is 64, 2 to the power 7 is 128. Right? Now, this is very important to understand. A typical binary number would be, this is a typical binary number. 11101110. Now, this is 1 bit. This is also 1 bit. This is also 1 bit. Total there are 8 bits. Right? These are total 8 bits. Right? What does this 0 represents? 2 to the power 0. What does this 1 what will we will write on this one? 2 to the power 1. On this one, 2 to the power 2. On this one, 2 to the power 3. This 2 to the power 4. This 2 to the power 5, and so on, right? Now, this is an example. This will help you in understanding much clearly. Convert the following binary numbers to denary numbers, right? These are binary numbers given: 0010, 1101. Now notice that there are 8 bits, 1, 2, 3, 4 on this side, 1, 2, 3, 4 on the left side. This can also be written as this with base 2, because we know that binary numbers have base 2, right? This can also be written like this. Now, how to convert it into denary numbers? Now, write it as follows: 0010, 0010, 1101, 1101. Write it as follows. Now, the headings, they've already understood the headings. Memorize it. 1, 2, these headings are powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. Right? We'll use it 1, 2, 4, 8, 16 like this. These are the headings. Right? 1, 2, 4, 8, 16, 32, 64, 128. Right? This is the example of an 8-bit binary number, right? Now, you have written the headings above each bit. Now, the ones add the corresponding numbers or values of bits that are on or 1. Right? The bits that are 1, which bits are 1? This, and this. Out of these 8 bits, these 4 are 1. Now add the corresponding numbers, values of bits that are on or 1. These are 1, 4, 8, and 32. Under these headings, the bits are 1. So add the powers of 2. For example, like this: 1 plus 4 plus 8 plus 32. We'll get 45. We can also write it as 45 to the base 10, because denary has base 10 and binary has base 2. Right? Remember, this is very important. Add the corresponding numbers or values of bits that are on or 1. In these 8 bits, these 4 are on or 1. Right? Now see the corresponding numbers of that bits. The corresponding value of this bit is 1, the heading, right? Corresponding heading of this bit is 4, of this bit is 8, of this bit is 32. Add all the headings, corresponding headings that are 1. You will get 45. Right? Now we are moving on to 16-bit. 1001, 1001, 1001, 1001. This is a question. Now convert it into denary form. Remember, the headings will be the same: 1, 2, 4, 8, 16, 32, 64, 128. Continue it. As 128, we know it's 2 to the power 7. When we'll proceed further, they will be 2 to the power 8, 2 to the power 9, 2 to the power 10, and moving on, right? So we get to 32768, which is 2 to the power 15, right? Now write these numbers, all 16 bits, under these headings, right? Now the bits which are 1, this is 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 one, this is one, this is one, and this is one. Now add the corresponding headings of those bits. This means 1 plus 8 plus 16 plus 128 plus 2048 plus 4096 plus 32768. You will get the Denry value 39321, right? Only those headings are to be added which have bits on or 1. Remember, the headings are always of 2, of power of 2. 2 to the power 0, 2 to the power 1, and like this, right? Now, next is from denary to binary. Convert the following denary numbers to binary numbers, right? The first question is 107. This is in denary form. What is denary form? It's a simple number form, right? 107 to binary. Binary is the language which computer understand. Denary, which humans understand, right? Now, we can convert this denary number into binary number using two methods. The first method is trial and error, right? Now, consider the conversion of the denary number 107 into binary. This method involves placing ones in the appropriate position so that the total equates to 107. Now, remember, when this method is to be used, always start from the left hand side. Now, we have mentioned the headings 1, 2, 4, 8, 16, 32, 64, 128, right? Now, we read this again. This method involves placing ones in the appropriate position so that the total equates to 107. The total must equate to the denary number given in the question, 107. Now, 128 cannot be, 1 cannot be placed under 128 because it has exceeded 107, right? 1 can be placed under 64, 1 can be placed under 32, 64 plus 32, we get 96. Still we are 11 behind. Now, we add 8, we are 3 behind, we add 2, now we are 1 behind, and now we add 1, so that we have completed 107. This is trial and error method, right? We have to place ones in the appropriate position so that the total equates to the number given in the question, right? The second method is the division method. This method involves successive division by 2. Because why we use 2 again? Because binary is 2. Binary system uses 2. The remainders are then read from bottom to top. This is important. Bottom to top to give the binary value. Now, when we are using 107, we get 107 divided by 2, we get 53 with remainder 1. When we divide 53 by 2, we get 26, remainder 1. When we divide 26 by 2, we get remainder 0, and the quotient is 13. We move on like this, proceed further when we reach till 1. Now when we will divide 1 by 2, you would get remainder 1. Remember that, right? When we will reach 0 and we will divide 0 by 2, we always get 0, remainder 0. Now, from bottom to top, read the read the numbers 0, 1, 1, 0, 1, 0, 1, 1, and write it in this form 0, 1, 1, 0, 1, 0, 1, 1. Right? These are two methods, trial and error and division. This is question 89, right? You must practice it after this, after watching this video, right? Now, Moving on, what are bits? We have already studied it. Binary numbers can be broken down into their smallest representation called bits. For example, 0, we are given a 4-bit, 0, 1, 1, 0, right? So 0 is a bit, 1 is a bit, 1 is a bit, 0 is a bit. How many total bits? 4, right? What is byte? Byte is a series of 8 bits. For example, uh, this one 00101101. This is 1 byte because there are 8 bits. Remember that byte is equal to 8 bits. Enough to represent one character A, B, 7 or R. For example, if we write A in computer, it stores 8 bits or 1 byte, right? Processed as a single unit of information. A single letter or character would use 1 byte of memory. A, for example, if we write A in computer, it uses 8 bits or 1 byte. And 2 characters, for example, if we write A and B, this will use 16 bits or 2 bytes, right? The smallest unit of memory in a computer is also known as byte. Many non-alphanumeric characters, for example, exclamation mark, dollar sign, and foreign language characters, Arabic, Japanese, use multiple bytes. That means more than 8 bits can use 9, 10, 11 or as many, right? Now, the right side of your on the right side, you can see the name of memory size, number of bits, equivalent denary value. Remember, now we are doing this. How the byte is used to measure memory size. Right? Now we are doing this. This has to be memorized. 1 kilobyte is 2 into 10, 2 to the power 10 bits. Then comes megabyte, which is 2 to the power 20. Then comes gigabyte, 2 to the power 30, and this moves on till petabyte. This is equivalent denary value. On your calculator, solve 2 to the power 10, you will get 1024. These are bytes, right? Now, you can also use, whether you use this or whether you use this, because we know that kilo is 1000, so we get 1000 bytes. Whether you use 1000 bytes or whether you use 1024 bytes, both are correct, right? But you have to remember the order: kilobyte, megabyte, gigabyte, terabyte, petabyte, right? If there is a question in exam which is smaller, kilobyte or gigabyte, right? So you must answer kilobyte because it has less number of bits or less number of bytes, right? You must memorize it. Now the last thing is computer register. A register is a small piece of memory built into the CPU of a computer system where values and instructions are temporarily held. Simply, a register is used to store bits, right? When computers or microprocessors are used to control devices, such as robots, registers are used as part of the control system, right? Right. In a digital instrument, a register might be used to convey whether the device is sending a signal to the computer 1 or 0. The instrument will have various registers to convey signals either way. I have already told you that a register is basically used to store bits, right? It can be a 8-bit register, right? Storing values 0011, 1101, right? Like for example this 0011 1101. This can also be stored in a register, which can be called a 8-bit register, right? We have this diagram with motor B, motor C, the direction of B and the direction of C. For example, the register is filled with these bits 1 0 1 0 1 0 1 0. Now what does this mean? This means motor B is on, motor C is on, B direction is forward and C direction is also forward. We're just talking about the bits that are 1. The bits that are 1 are working and the bits that are 0 are not working. So what does this mean? Motor B is working, motor C is working, B is directed forwards and C is also directed forwards. So what does this mean? This means that motor B is on, motor C is on. Both motors B and C are turning to produce forwards motion. The direction of both B and C is forwards. So hence the statement is the vacuum cleaner, or in this case this is the register of a vacuum cleaner, right? So that means the vacuum cleaner is moving forwards, right? Now we are going to do some past paper questions which are end of class questions. Today we will be practicing 5 questions from past papers. This is the first question. Computer memory size is measured in multiples of bytes. 4 statements about computer memory sizes are given in the table. Tick to show if the statement is true or false. Right? Now, what is the statement? This is a past paper question. Right. 25 kilobytes is larger than 100 MB. 25 kilobytes is larger than 100 megabyte. This is false because MB is greater than kilobyte, right? Now, remember, you have to memorize this. 1 megabyte is 2 to the power 20 bits. 1 kilobyte is 2 to the power 10 bits. 1 gigabyte 2 to the power 30 bits, 1 terabyte 2 to the power 40 and 1 petabyte 2 to the power 50 bits. Kilobyte, megabyte, gigabyte, terabyte and petabyte. Right? Now 999 MB is larger than 50 GB. This is false. This is clear cut. Right? 3500 kilobytes is smaller than 2 GB. This is true. Next, 2350 bytes is smaller than 2 KB. What is this 2350 bytes? There is no K here, no M here, no G here. That means that 2350 bytes is 2.350 kilobytes. This means, what does 2350 bytes mean? This means 2.35 kilobyte. So now read it like this. 2.35 KB is smaller than 2 KB. No, that's false, right? So this is how you solve these conversion questions, right? This is very important. Now, this was worth 4 marks. Moving on to question number 2. An 8-bit binary register. This is a register, right? Which uses 8 bits. 0010, 0100. Now the question is, convert the binary value to denary. What we will do here, we'll make headings. 2 to the power 1 is 1, 2 to the power 2 to the power 0 is 1, 2 to the power 1 is 2, and here 4, 8, 16, 32, 64 and 128. Now how will we convert this binary value, which is 0011 0101, to denary? We'll convert it. Remember, first we'll underline the bits that are ones and then add the corresponding headings of those. So now it will be 32 plus 16 plus 4, which will be 52. You can write it like this. 52 to the base 10. Remember, denary has base 10 while binary has base 2. Now, the next is the contents of the register shifted one place to the right would give the result. The contents are the bits of the register. For example, if this 0 is shifted one place to the right, this will become 0, right? If we talk about this 1, if it is shifted to here, it will become 1, and this one will be shifted here, right? It will move on and on, right? So it will be 0 0 0 1 1 0 1 0. We will start from right and shift it one place. When this will be shifted one place to the right, this will come here, and the previous one will take its position. This will be 0 0 0 1 1 0 1 0 when we shift it one place to the right. Now the question is, the contents of the register shown at the start of the question 4, that means this question, are shifted two places to the left. Now show the contents of the register now. 0 0 1 1 0 1 0 1. Now every bit is shifted two places to the right, right? So what will it show? This will be 1 1 0 1 0 0 0 0, right? How? For example, if we take this one, when we shift it two places to the right left, it will be 1 2. So this one will come here in this position, this one will come here in this position. This process will be continued 1 1 0 1 0 0 0 0, right? Now state the effect this shift has on the denary value on part A. For example, in part A the value is 52. Now calculate the denary value. This will be 1. Calculate the denary value of this new register after the shift has taken place. This denary value will come 208 after the shift has taken place, and the initial one was 52. So the effect is, what effect has it created? The denary value has been multiplied by 4x, 4 times. This is the effect, right? The next question is question number 3. Different units of data can be used to represent the size of a file as it changes in size. Fill in the missing units of data using the list given. We have 4 things: byte, gigabyte, megabyte, and nibble. Now nibble is a new thing. What is nibble? Nibble is equal to 4 bits. Nibble is 4 bits, which is half a byte, and byte is 8 bits. Now byte is 8 bits and nibble is 4 bits. Nibble is half a byte, right? Now the units of data increase in size from smallest to largest. Smallest to largest. Now first is given bit. What comes after bit? What comes after bit? A nibble. Nibble comes after a bit. What comes after a nibble? A byte, because byte is 4 bits more than a nibble. After a byte comes kilobyte. After a kilobyte comes megabyte. Right. After a megabyte comes gigabyte. And after giga comes terabyte. So it's important, very important to memorize the memory size table. Right? This was worth 4 marks. Question number 4. Yes, this is question number 4. This is the left side is A part, the right side is B part. 6 marks question. A stopwatch uses 6 digits to display hours, minutes, and seconds. The stopwatch is stopped at when the time is 2 hours, 31 minutes, 58 seconds. An 8-bit register is used to store each pair of digits. Write the 8-bit binary numbers that are currently stored for the hours, minutes, and seconds. Now, I have already told you before that denary numbers are normal numbers which humans use. So this 2, this 31, this 58 are denary numbers. And now we are asked to write it in binary numbers. Oh, sorry, binary numbers. So simply we have to convert from denary to binary, right? So the ours is 2. How will we convert it to binary? Simple. While the headings are 1, 2, 4, 8, 16, 32, 64, 128, right? The R's will be 0, 0, 0, 0, 0, 0, 1, 0. These are R's. Because when we write the headings 1, 2, the 2 is 1. That means we will add 2 to all zeros. That will be 2. The minutes is 31. By trial and error method, as we used in the R's, now place ones in the appropriate position so that when we add the corresponding headings, the answer becomes 31. That will be 0, 0, 0, 1, 1, 1, 1, 1. For seconds which are 58, the answer will be 0, 0, 1, 1, 1, 0, 1, 0. Right? We just have to convert this denary 23158 from to binary. Right? The B part, the stopwatch is started again and then stopped. When the watch is stopped, the 8-bit binary registers show. Now, hours, minutes, and seconds are given in binary format, and you have to convert it into denary. Right? How will we do it? Just as we did it in the lecture. Now, hours, we will give headings 1, 2, 4, 8, 16, 32, 64, 128, and see, underline the bits that are 1. For example, in hours, the bits that are 1 are these 2. What are their corresponding headings? 1 and 4. Add these, we get 0, 5. For minutes, we have this, this, and this. Add the corresponding headings, so you will get 26. For seconds, we have 1, 2, 3, 4, 5. Add their corresponding headings and you will get 55. So this is the new time, 5:26:55. The last question is question number 5. The denary number 57 is to be stored in 2 different computer registers. Convert 57 from denary to binary and show your working. So you have 2 methods, whether you do it by trial and error as we did here in this question, or you do by division by 2. Now what does this two different computer registers mean? Now what does these two different computer registers mean? This register and this register, which is given in part B. But first we have to convert from binary to binary the number 57 as we did here, right? Now the B part is show the binary number from part A as it would be stored in the following registers. Remember, this is a 8-bit register and this is a 16-bit register. Both of them are included in your syllabus. 8-bit register will be the answer that you got here. 0, 0, 1, 1, 1, 0, 0, 1. Now for 16-bit register, when you have to show 57 in a 16-bit register, remember the bits to the left will all be 0, right? Now copy this in the 8-bit register. For example, if this 1 2 3 4 5 6 7 8 and then 1 2 3 4 5 6 7 8, this side, these are 8 bits and these are 8 bits. In this register 1 we solve 57 in a 8-bit register. This will be copied in the right side of the 16-bit register. Now on the left side, the left 8-bit register will all be 0, because if we add any of to any of them the value of 1, the 57 will be increased to some other number. So these all will be 0, so as to have no increase or decrease on the value of 57, right? Part C, a binary number stored in a register can have many different uses. For example, an address in main memory. Give two other uses for a binary number stored in a register. Use 1 can be data. Used data. Now the use 2 can be a character. I'm writing it as CHAR, or a number. Sorry. Or a number. Data, character, or number, right? These are uses for a binary number stored in a register. It can show data, it can show a character or a number, right? We are done with today's computer science class. We studied binary systems and we have completed the chapter binary systems. In the next class, in the next computer IGCSE GCE computer science series, next class we will be studying hexadecimal number system. So we are done with binary systems. These 4 points are done. We have studied these 4 points and done their past and I've done their past papers. I'll meet you in the next class. Till then, Allah Hafiz.